So thanks for the invitation and actually the opportunity to give this keynote talk here. I'm really glad to see such a workshop actually, and also the accompanying challenge here coming up now, because I've been like sort of around in this field and like working on this problem of generating verbal non-verbal behavior for quite some time now, and it's really great to see like there's like a new wave of young ambitious people coming with fresh ideas into the field. So I thought I could take the opportunity to talk about like what we learned after 25 years of research where we are in the field, and also probably like to give an impression of actually where we came from and what are their like original ideas. So but let me start with the problem definition. So what are we talking about? So even though the workshop is on nonverbal behavior generation, I thought I would like to take to look at the slightly bigger, larger problem, namely multimodal behavior generation. So what does it involve? Like by and large, 3 steps, right? So let's assume we have a communicative goal. That's sort of like the normal starting point in all of our intelligent virtual agents, social robots, our artificial interlocutors. And given such a communicative goal, we have to basically, in multimodal behavior generation, we have to solve 3 problems. The first one is we have to select modalities, actually, which we want to use to perform certain behaviors in order to achieve this goal. This could be speech, like spoken words, along with prosody or intonation, facial expression, gaze, different kinds of gestures, and so on and so forth. The second problem, obviously, is within and for each of these modalities, we have to generate behaviors, sub-behaviors. Obviously, we have lots of different options within each modality, different ways to, let's say, convey different kinds of information or to achieve different communicative goals in different modalities. And that's already a lot of like very hard complex within each modality on their own right. And then finally, obviously, we have to combine these behaviors or sub-behaviors and adjust them to each other. And to each other means to the behaviors in other modalities, which are supposed to like accompany each other, like here the yellow or orange lines here, but also adjusting them to each other, like to subsequent behaviors within the same modality in order to achieve like an overall natural flow of behavior. And I think it's really important to note here that these sub-problems cannot be tackled independently of each other, right? So given a certain communicative goal, I might have a specific modality which offers me a nice behavior in order to achieve, like, say, a part of its goal. Therefore, I will take this modality and then generate this behavior, right? That actually might then impose constraints on other modalities or other behaviors, and which might then in turn lead me to change or adapt in the first behavior in the first behavior. So that actually is what makes this problem so hard and so difficult, but also so interesting. And we started, and the whole work basically can be traced back, and maybe started with this famous animated conversation system by Justine Cassell and colleagues, back when they were at the University of Pennsylvania, and when they published it in 1994 at SIGGRAPH. And what they did was they just did sort of like a procedure approach to synthesize and animate a conversation between 2 virtual characters here, Gilbert and George. I'm talking about, let's say, a bank counter situation, talking about opening a bank account or like offering a check or something like that. And what they did is, that was the first system basically combined multiple communicative modalities. So they looked at speech and prosody, they looked at gestures, hand gestures, facial expression, gaze, head gestures. And for each of these modalities, they came up with like specific, let's say, rules, like a model for how these modalities can be used and also how they could be combined in order to achieve a given communicative goal, which was given by a dialogue planner. So they compiled a wealth of knowledge from different disciplines, most notably linguistics and dialogue research, into some like symbolic rules that could be executed before. They were like represented in a graphical way, so they had networks, but then they were compiled into scripts and so on and so forth. And that flow actually here then like comprised 2 different steps. The first one is dialogue planning, like planning the communicative goal or intent, also deciding on what behavior forms to pick actually in order to achieve it, and then finally to realize that behavior, mainly playing like synthesizing the speech or animating the movements and so on. So after that, there were years of growth, right? So like the late 90s, then the early 2000 years, the first decade of this century, We saw a lot of systems, a lot of work on virtual agents. Also, social robots became more commonplace, and they also started to look into behavior generation. And what we saw is there was an increase in different modalities being considered, obviously, but then at the same time, people have started to look more closely at single modalities. They came up with more sophisticated models for single modalities, and then tried to combine very few of them on a more sophisticated basis, maybe like 2 or 3 modalities together. We also saw a lot of toolkits coming up and also architectural principles for like the full-blown agents, basically, but also for multimodal generation, as well as, for instance, multimodal fusion. So when it comes to recognizing and fusing and interpreting multimodal behavior performed by the human interlocutor, for instance. And then in 2005, a bunch of people met for the first time in Reykjavik, and then we decided, okay, because in 2004, at a workshop at the AIMS conference in New York, we had the impression that there is, many people are working on it, but it's really hard actually to bring these bits and pieces together. So people are working in different modalities, and the whole endeavor is so daunting to build like an embodied conversation agent, like a human-like expressive artificial being, so to say. It's really indispensable actually to bring work together, to fuse work together. But this is really hard without having like a common understanding of what are the processing stages, what are the processes, and most importantly, what are the interfaces between them. And therefore, we met in Reykjavik, and this was like Chris Horason, Richard Kent, Bruce Johnson, Norman Badler, Stacey Marcella, Hans Williamson, Joe, and myself. And we hang out for a couple of days, and we decided to structure this generation problem and to define interfaces. And the 2 interfaces that most of you are aware of are, I think, so these 2 markup languages, BML and FML.
Okay, so going back to the BML, FML idea. So the idea was to, this was sort of like what I would call like the lowest common denominator. So people have been working on multimodal behavior generation, and we just looked at, okay, what could we agree on? What are the different stages that we have to work on? And that are, of course, like figuring out what to communicate, like intent planning, like planning this communicative goal, then planning the behavior actually that we need to perform or to achieve this goal, which what's called behavior planning here in the middle, and then finally to actually execute it, which is what we call behavior realization. And for in between these stages, we defined this interface languages like function markup language and behavior markup language. Behavior markup language basically is meant to be the interface between behavior planning and realization, and just specifies the kind of behaviors that the agent is supposed to perform, and also like synchronization constraints between them. Function markup language was supposed to be the representation of this communicative intent and to serve as sort of like the base and starting point for behavior planning. FML has never been clearly consolidated or specified, to be honest. Behavior markup language, BML, did quite well and has become sort of like the quasi-standard in the field. What it is, for those of you who don't know, just let's spend one quick slide on it. It specifies it's a markup language, and it specifies behaviors. So it allows you to define behaviors in different modalities. So it covers the main communicative modalities. You would put these behaviors into what's called behavior block. Like in this case here, for instance, you have a speech block, a speech behavior saying, okay, welcome, ladies and gentlemen. And you have a gaze behavior, which you want to have like a directed gaze towards an audience. And what you do then is, well, you can impose synchronization constraints, saying that you would like to have the speech start at when the gaze is ready. And for that, we define synchronization points within each kind of behavior, nonverbal behavior, like start, ready, the stroke phase, the meaningful phase, and the end and relax phase, for instance, here, right? And you can refer in other behaviors and other modalities to these sync points in order to specify synchronization constraints. You can also specify how different behavior blocks, which are supposed to follow upon each other, are supposed to combine, right? You could merge them, you could have like one block overriding the previous one, and so on and so forth. Okay, so now, and then there have been a lot of behavior realizers, and they are still being used and still being developed that actually are supporting the standard. And they have been developed with different, let's say, goals in mind. You have Smart Body, part of the Virtual Human Toolkit from ICT in LA, where the focus is on realistic behavior, and they use a lot of artists to design the behavior and to record motion capture movements in order to really perform high quality and to achieve high quality agents. You have other realizers like Lightbody from Northeastern University in Boston, or Greta from Catherine Pelachot's lab, which focus on, for instance, expressivity or robustness. We have realizers now for robots, also included in the ROS standard, for instance, and we have realizers that focus on flexibility and being able, for instance, to change behavior, to interrupt behavior, to adapt behavior, still during execution time, for instance. So in order to enable like a very responsive agent, responsive interaction, for instance. Okay, so that's where we are right now. So now if we look at what followed then we can actually say there are two main approaches to multimodal behavior generation. The first one is, and that was like the earlier one, is we assume that we have a communicative intent, like the orange box up here. That's sort of like the communicative goal. So it's a specification of what communicative goal the agent should achieve with this communicative behaviors. So it's usually a communicative intention and also some content that needs to be communicated, plus some contextual factors like the affective state of the agent, the social context, the relationship between the agent, and so on and so forth. So what you have to do then in multimodal behavior generation is you have to implement modality-specific mappings, like this FM1 here or FM2 for different modalities, and in order to map, let's say, parts of this intent at least into a specific behavior, B1 in this modality and B2 in this modality. And you have to like coordinate these two, obviously, in order to make a consistent multimodal utterance. So often this is done prior to realization, and different approaches have been used for that. The second approach that we see more recently is to go for cross-modal mapping. So taking one modality as given, like in this case here, let's say assume we have B1 given, and this is normally speech or text. And then the question is, okay, let's implement a mapping like FM1-2 here from this behavior to other additional behaviors that could go along with it, like from verbal behavior to non-verbal behavior, right? So sometimes people go for this direct mapping from behavior in one modality to behaviors in other modalities, or they try to invert this mapping here in order to sort of like interpret this behavior for aspects of the underlying communicative intent, which can then inform the generation of the other behaviors in the different modalities. So usually this comprises realization because the behaviors that people work on and the data that is available now in order to approach the problem this way, like involve like lower level features like movements, motion capture data, acoustic features of a synthetic speech, and so on and so forth. So realization is for some part already involved in this mapping. Okay, so let's have a look at the different approaches that people have been taking in these two different directions. So the first one is, let's say, intent-driven behavior generation. The easiest and therefore most like popular approach in the early days, at least, was let's just use a lexicon. Let's just treat nonverbal behavior as if it were words that could be lexicalized. So meaning we could like demarcate different, let's say, signs, nonverbal signs. We could assign them a unique, let's say, functions, and then we can just retrieve them from a lexicon, select them from a dictionary, if you will, based on parts of the intent, and then we can just use it. So people have started to, for instance, define gestures in terms of a gestionary or gesticon, right? Then given some context-sensitive selection rules, obviously taking the intent as an input, people pick from that lexicon and then combine these gestures together or with speech based on some rules, templates, or even like in a grammatical framework. Often it's not like a fully predefined gesture, but templates in this lexicon, and then there is some parameterizations still to be figured out in order, for instance, to modulate expressivity or to adjust gestures in order to better fit speech or to better like fit in the fluent flow of behavior, for instance. So this is obviously a limited approach, but practical, that's popular and useful mainly only for representational symbolic gestures, namely gestures that could be lexicalized, right? So like signs.
Whatever works for you, that's for you. But please do not tell me what works for me. Would you please just mind your own business and I will mind my business. And let's get on with our lives.
So that was an example from Katri Pelachot's lab based on this approach in the GRETA system. The more heavyweight approach would be to go for more flexibility by really building and constructing these nonverbal behaviors. In this case, again, gestures. So by planning them. So like planning-based approaches like this, for instance, here that we developed when I was like postdoc doing together with Justine Cassell in the States, what we call multimodal microplanning. So given that we have a communicative intent, we try to build and construct and plan a gesture, like an iconic gesture, that would convey or depict the important salient spatial or geometrical features of this, let's say, mental image that the agent might have in mind. And then we had to, and that again used like an extended grammatical framework, then we had to insert that into speech planning. And then the speech was planned and the gesture was basically like introduced into the speech planning as if it were like a lexical constituent. So then we had this syntactic tree here, and then that was again realized using BML compliant realizers here. The domain was direction giving, and that worked quite well for pointing gestures and iconic gestures, which we could really compose out of different features. So there it would be like, but this means to assume, for instance, that is like a grammar of multimodal behavior, which isn't fully adequate in my opinion right now anymore. But at that point, and given for a certain kind of, let's say, multimodal constructions where the gesture could like attain a specific role as if it were a constituent, that works quite well. Then we also see a lot of, the data come up more and more, and then people have started to look at the data, right? We did, for instance, an approach where we use the Bayesian decision network to do this gesture planning. So based on data, so how actually really people use their hands in order to depict like spatial features, for instance, in their iconic gestures, we built a Bayesian decision network where we added certain modeling assumptions about, let's say, the iconic mapping from certain, let's say, spatial features of an object that you would like to depict gesturally to hand shapes or hand orientations, but also how these different features affect each other and how those decisions are affected by features of the referent object, by the discourse context, or by the previous gesture, for instance. That was learned statistically from a huge corpus with more than several thousands of gestures annotated for form, meaning, discourse context, and so on and so forth. And here's like an example of such a network, and you could, just like a probabilistic inference problem, you would insert what you have as an evidence, and the network spits out a specification here of features that the gestures should have, and which then needs to be passed on to behavior realization, and then in order to create a full gesture out of this. That obviously is part of a bigger generation architecture. So what I just described to you is like this middle layer here, which is this behavior planning, right? It assumes that you have a previous stage, the blue box here, where the intent is planned. So like the features that need to be gesturally depicted, the propositions that need to be verbally communicated, and so on and so forth. And afterwards, the green box here, as I said, a realizer that takes such a specification and is able to produce a gesture out of it, a gestural movement, along with synthetic speech, and synchronizing both of them, for which we use some of these realizers that I just showed you a couple of minutes earlier. Okay, so intent-based gesture generation up to now, summary. So we see model-based and data-based approaches, and they to this gesture planning, let's say gesture formulation problem, as well as to the gesture realization problem. And they all lend themselves differently well to different kinds of gestures. So learning-based, data-based approaches succeed most when it comes to producing motor or beat gestures or discourse or interactive gestures, like the speech gestures here. Planning-based or lexical-based approaches, they are suitable more when it comes to producing representational gestures like iconic gestures, pointing gestures, emblematic, symbolic gestures, and so on and so forth. And whether they rely on procedural animation and more compositional approaches or more on templates and animation primitives, it's just a matter of taste and whether whether you're willing to invest all the effort in order to achieve, let's say, more flexibility here and to be more to be better able to convey, let's say, more complex semantic messages. Second approach, and the one that I think most of you guys are actually also working on right now, is obviously this speech-driven approach, right? So you have a speech signal and you try to communicate, you try to augment it with other nonverbal behaviors. So I think there's two basic roads that could be taken there. As I said already, right? The first one would be, let's call it M2M, modality to modality. You take a modality, normally that's speech or language or text, and then you try to come up with a solution for the mapping. How can I map that input modality to other nonverbal modalities or behaviors in different modalities? The second approach would be M to I to M, from modality to intent, and then back to the other modality. For this, you would have to invert this mapping here from intent to behavior. Now, I think it's important actually to note that although we have a lot of people working on this, although we actually see really remarkable and really impressive results there, in principle and in the general case, this is an ill-posed problem. So let's assume that we have a communicative intent, and let's assume that the full multimodal utterance actually is the solution actually to, in its entirety, communicate this intent. Yeah, then actually it must be theoretically an ill-posed problem actually to start from a part of this multimodal utterance and then try to recreate the additional parts. That can only work to the extent that there are redundancies and strong correlations within those modalities, which they are, which we see, right, in current approaches. But in general, and when it comes to all communicative functions, for instance, I think this is an ill-posed problem. So in this, let's say, in this direction, people have been doing like different kinds of approaches. Again, the earliest systems, like the famous Behavior Expression Animation Toolkit or BEAT system, also published at SIGGRAPH 2001, uses rules, right? So you input some text here, you do some language tagging, also based on discourse model, for instance, in order to figure out where the new information is, with the so-called ream in information structure theory, and where the old information is the theme. Then you have rules to suggest behaviors. This system would normally overgeneralize, so it generates a lot of behavior suggestion. Then they are filtered out, and then in the end they would be scheduled, and then you have a script. Then again needs to be passed on to a realizer in order to perform the animation and the synthetic speech, for instance. More recent systems, 2013 here, Lomea and Stacy Marcella, basically use a similar pipeline, but they also use, for instance, here acoustic processing of audio features of the incoming text. Then they apply a lot of rules or models in order to assign different communicative functions to this text. So try to recreate parts of this intent, what we just talked about. And then again, use that function to map to behaviors, which are then again spit out as a BML, like scheduled, and then spit out as a BML script to a realizer. But then, obviously, more recent approaches, they use data and data on multimodal behavior in order to learn a mapping how different features from one modality, behavior one modality, correlate with other features in the different modalities. Some earlier work, like here from Matthew Stone and Dr. Carlo, they use what might be called multimodal unit selection, and that is actually data-based in the sense there is no model being learned, but there is a huge repository of segments, like a big database, and given certain a script and certain constraints, the system would, just like unit selection in speech synthesis, would just pick selection units from speech and units from motions, basically, and stitch them together while optimizing for certain cost functions. In this case here, you optimize for seamless speech on the one hand, smooth motions on the other hand, and at the same time a consistent timing between these two modalities, for which they need to mark the moments of emphasis, basically, in both modalities. Michael Neff and Michael Kipp and colleagues, they came up with a model where they use the data not as a repository, but in order to learn something. And in order to learn, let's say, a model that actually then could help to inform the production process. And here, what they learn here is they have video corpus, they annotate it manually, and then they statistically learn profiles. Gesture profiles, for instance, of different kinds of speakers, and very distinct speakers in their case. And then they use those gesture profiles and mappings from word to semantic context and then back to gestures in order to do the same thing as before. You put in some text plus some discourse features, information structure here, discourse structure, and then you apply those mappings, and then you have a gesture script that then can be animated, basically. And then finally, we have the learning-based approaches, so where the data is really now being used in order to learn models of this mapping from one modality to other modalities, right? Which means predicting, for instance, gestures from speech. And an earlier approach, again, Stacy Marcella and together with his colleague Chu, they learned a model that actually was basically they tried to learn a model that maps from a motion frame, a previous motion frame, to the next motion frame. So a model of gestural movements, if you will, mainly for non-representational motor gestures, beat gestures, and so on and so forth. But then to modulate that mapping based on prosodic features of simultaneous speech, basically. And what they were able to achieve looked like this.
Listen to me!
Listen to you by what right?
By divine right, if you must. I'm your king.
No, you're not. You told me so yourself. You said you didn't want it. Why should I waste my time listening?
Because I have a right to be.
Yeah. So what we see is it's really just this motor movements, basically just this jerky beats, but they are nicely synchronized with the pitch accents and the stresses in the prosody of the speech. In later work, they used together then with LP-MONC, deep learning, and also second-order conditional random fields in order to predict not just motion frames, but in this case on a higher level of abstraction, whole gestural signs, if you will, right? So they look at whether can we really predict a whole gestural sign based on words plus prosody plus some syntactic information like part of speech. And they found that actually it's this deep architecture here that actually brings the biggest improvement, not so much this temporal ordering here in this conditional random field structure that helps to achieve a quite good accuracy, but which again only achieved 59% here. So, and then it really took off, right? So this learning-based approaches here. Now we see a lot of people working in this, looking at behavioral data from motion capture data or video data from YouTube videos and so on and so forth. And they all apply really modern machine learning approaches like variation autoencoders, deep learning, LSTM networks, and so on and so forth. There's a lot of experts in the audience who know better about it than me, I'm sure. Trying to predict mostly gestures from speech, for instance, right? Well, or more specifically, body pose sequences from audio features at first here, with a focus on really naturalness and also some temporal or semantic consistency, plus maybe some individual style. And what we see here is so here's, for instance, an example of from the Hasegawa et al. 2018 paper here. So the orange bar is a prediction and the blue bar is our original behavior. We see a very good naturalness, but not so good like consistency. So the model is able to create very natural behavior, but the consistency when it comes to consistency with for instance, speech is okay, and it's better than mismatch, obviously, but it's not as good as an original in the human data. So more recent work even then also included not only audio features like spectrogram or MFCCs, but then also additional linguistic features, most notably word embeddings. So taking the words and the text and then doing some embedding. And also using this input features for the mapping to gestures. And then again, we see good results when it comes to likability or naturalness and so on and so forth here. But keep in mind that this actually is here work where they created gestures and then map the gestures to the robot, to the now robot here. But the speech gesture correlation is still not perfect here. It's really like worse than ground truth, for instance. So summary. So I think speech-driven gesture generation, made a lot of great advances, and I think there's more to come through this learning-based techniques. And actually for both, right? For this modality to modality mapping or for this modality to intent and then back to the other modality mapping. And there's obviously great strengths there, right? So we have like an automatic behavior enrichment through really realistic and temporally aligned interactive gestures. And I think the biggest strength here of this approach is really when it comes to this interactive gestures, speech gestures, for instance. And those approaches have proven actually to be able to increase naturalness, likability, and believability of behavior. Right? So this could be a really big, and is actually already a big progress in terms of behavioralization when it comes, for instance, to creating avatars or enriching them non-verbally and so on and so forth. But I think they also have limitations, right? So the biggest limitation is, of course, it requires a driving modality, which is always speech or language. So it's speech-driven, right? Now, this modality is taken as an input. That means it's excluded from the generation process. So multimodal or cross-modal coordination thus only works in one direction, right? So we only take speech and then we add nonverbal behaviors to speech and make them such that they fit the speech, right? This is okay, and this is reasonable, but this is not actually what happens like in nature or in humans, right? When we actually produce both modalities at the same time and both modalities are adapted to each other in one way or the other. Second, given the data that we have and that people use, and this is mostly like behavioral data only, and obviously it's really hard to get like a lot of data where you have like ground truth annotations of communicative intent. They tend to rely strongly on learned association or correlations between surface level behavioral cues only, right? And it's therefore inherently limited for generating representational gestures because it's really hard to have a full understanding of the intent, if not even ill-posed, as I said before. And then again, to have a mapping from that intent to the other behavior, like gestures in this case here, for instance, because that is not being considered. That's not represented in the data and not being considered in the learning problem. So the field's developmental path could be maybe possibly visualized like this. So we can say, we can go for, when we want to do behavior generation, we can go for naturalness and human-likeness of the behavior, right? So let's this be this axis here. But we could also go for what I would like to call communicative efficacy. So in terms of, can the agent really flexibly get across what it needs to communicate? So can the agent really flexibly respond to the needs and the demands of the communicative situation and make sure actually that the addressee really understands what it needs, what she or he needs to understand. So, and starting here in the early days, actually people have really worked towards this communicative efficacy or efficiency. And that was when people have worked on this intent-driven and planning-based approaches. But naturalness and human-likeness was not very good at all. Actually, there's people in psychology, for instance, Jim Blazkowicz, who argued for communicative realism as opposed to full human-like realism as actually the more important factor to optimize for. Meaning communicative efficacy and communicative realism is more important than really reproducing naturalness or human-like emotions. Nevertheless, people have started and have tried to work towards naturalness more, and then have started to obviously do data-based and then later on learning-based approaches. And here's also where the speech-driven approaches can be located, I think. And the question obviously is also, so since let's say since the field developed along this path, can we get back up here, right? How do we get here? And there's a lot of questions actually that we need to and can actually discuss now. What we need to be working on actually to get there. And the core question obviously is, what are features actually that are important to take into account, right? as an input, which features need to be there as an input, which features need to be like reconstructed out of the input or as a hidden features, and what features actually need to be mapped to as an output. And which models and techniques actually can capture this? And is it actually sufficient only to include like additional, let's say, features in the data? And will the model actually then already pick up on that? Which is what people do, for instance. Or will we need to have like fundamentally different kinds of models actually? And finally, which data and theories to draw from and now in order to help us actually let's say also to get beyond only the level of surface level behaviors. So challenges in perspective then, from my view. I mean, the ultimate goal for socially intelligent agents and embodied conversational agents, and this is like my main perspective, right? You could well say, okay, I'm most interested in producing, let's say, natural looking avatars for computer games, for instance. But if you really want to build like social intelligent agents or embodied conversational agents like the IVA community or the social robotics community, then communicative realism and efficacy is the ultimate goal. So multimodal behavior generation must enable that. So for that, we need to have agents that are expressive, self-consistent in themselves. So the modalities need to fit each other. But also the way the modalities are being used need to fit, like to produce a consistent identity of the agent, also culturally and contextually shaped. And they need to be socially cooperative. And by that I mean they really need to be able to engage in an interaction, to respond to the needs of the addressee, to adapt and flexibly like change their behavior on the spot. And that actually means that multimodal behavior generation must account for the fact that the behaviors are optimized for serving social communicative functions, first of all, and that they are coordinated on the spot to fulfill speaker and addressee needs, that are shaped by the current social interaction context, and as I said before, they differ, and they differ largely, yet in some way consistently, between tasked individuals and cultures and so on and so forth. And that's actually what we saw in a lot of studies, that we see a huge individual differences in the way how people, for instance, behave non-verbally in social communication situations. So what we need to do actually is we need to go for what I would like to call interaction-aware behavior generation. And I don't know how I'm doing time-wise, Taras?
You should wrap up quite soon.
Okay, so I was going to present you a couple of examples, and I will just like rush over that now, in order to convince you of the importance of this point. So here, for instance, like we have strong interpersonal alignment, right? The way people use their behavior is dynamically and shaped and affected by the behavior that that the interlocutor is performing, right? So people align on spot dynamically. And we also see this, for instance, in human-agent interaction, right? We have done studies where we see the way people use their hands actually is directly affected by the way, like the agent they are interacting with uses its hands. I'm going to skip this one here. And also and then talking about the features, which features do we need to take into account in order to inform and control multimodal behavior generation, enable it? The question is obviously, what are the functions that really matter, basically? And also from the point of view of the addressee. And we did studies actually where we presented people with such a gesture here, and this is just like this 200 iconic gestures, and we asked people, what do you see? What is this gesture doing actually? And what you find is that you have like different clusters of functions that gestures actually serve, namely representational, of course, like depicting size, referring to objects and numbers, spatial, of course, referring to places, localized events, depict movement, but then also meta-communicative, like signal prominence, signal uncertainty, and so on and so forth, right? And see, when we saw these clusters here, that is what people actually go for when they look at gestures and what they try to fit, or what to take out of gestures and how to interpret their meaning, basically. And there is actually, and in a follow-up study, we did a study, a similar study, and we looked at the gestural forms that we see, and we do see some some typical gesture morphologies or features that people use, for instance, here, when they are trying to, let's say on the right-hand side, when they try to focus something. So that's a very strong, let's say, pragmatic function of a gesture, emphasizing something or de-emphasizing something, or signaling that actually people are not really certain about what they are, or uncertain about what they actually are talking about right now. So there is actually functions. There's only very little theory about it. And also the relation of this and the importance and the relevance of these functions in agents and human-agent interaction has not really been looked at very much. We did a first study actually where we synthesized such a behavior and we looked at whether people are sensitive to it, and also not by just asking them, but also by asking them, so what do you recall of what the agents just explained to you, told you about? And we see a better recall when the agent actually focuses things, and a weaker recall when the agent actually signals non-verbally uncertainty, for instance. All right, so since I'm told to wrap up, conclusions. So some trends, previous trends and also current trends in multimodal behavior generation. So people started out from many modalities, then they narrowed it down very much to single modalities, with sophisticated models for them, and then started to recombine them, but only very, very few modalities. Speech is the driving force in generation. We saw this big trend from rule planning based to learning from data approaches, from categories and forms now to functions, and there's a lot of functions, and they're coming back into the picture, I think. But also important is now to see that there's a trend from single behavior units to streams of fluent behavior, and from single speaker behavior, like a monological behavior, to behavior that is really embedded in a social interaction context, right? So final slide. I think the field has explored a variety of modalities, techniques, interaction architectures. And we still see new approaches being applied and developed, right? Whenever there is a new model in machine learning, people are applying it also to this behavior generation problem here. So we are still extending our repertoire, mostly for very specific generation problems. But still, we also need to consolidate our views actually on what we can generate, whether only increasing the data, for instance, will help, how we can join the different approaches that have been out there, and what we should optimize our models for. So I think it's really good that this workshop also looks at evaluation measures here, because it's really hard to tell what is a good behavior quality, for instance, when is the output of a model actually suitable or not. And also in linguistics and language, there is what people call felicity conditions. So conditions under which a certain behavior works well, right? So I think there is a big question actually, what are good metrics and evaluation measures here used to not only to judge the output of a model, but maybe also sort of as a loss function to use them when optimizing those models. And finally, I think we need to enable really interaction-aware behavior generation. By combining learning-based with model-based approaches, we need to reconsider all the functions, the intent. We need to learn from data on interactive behavior couplings. And actually, we need to employ more online incremental learning for this. And with that, I thank you for your attention.